Welcome to Puzzles to Exercise the Mind, Lesson 13. Our first puzzle is an arithmetic problem. We have this shape here with 10 circles, and we're going to fill each circle with a number from 1 to 10. We can't reuse the numbers. And then we have these conditions where you see these different lines here. So the numbers you put in here and here would need to add to 12. These three numbers to 27, these four numbers to 13. Then you have this sum here, 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 and here. So all of those different sums indicated need to be fulfilled when you place the numbers in these circles. I'll give you the answer at the very end of this lesson. There's a few things you can do to eliminate the number of possibilities. I'll just give you one hint here. Again, the number's going from 1 to 10. So if these three have to add up to 27, the only way that could happen is if you have 10 plus 9, that's 19, and an 8 is 27. So 8, 9, and 10 need to appear. Now we don't know what order they appear in, but they need to appear here in these three circles in some order. So if you do that type of analysis in other places, you'll start to be able to deduce what the numbers are, and then you can complete the puzzle that way. So you don't need to guess. My point is you can deduce some of the numbers, or where the numbers are placed based on these different constraints here. I have a puzzle from this book that I've referenced a few times. Put the reference down here. It's known as the Castle Guards puzzle. I changed the wording a little bit from what was in the book, but it's essentially the same puzzle. So you have 9 towers along a wall surrounding a castle, so it's a closed loop. And there's one guard stationed at each tower. Normally, every hour, each guard moves to the next tower in a clockwise direction. However, one evening, the guards are a bit disoriented. They continue to move to an adjacent tower each hour, but in a random manner. After several transitions, all the guards are at the same tower. What is the minimum number of hours for this to happen? Another way of looking at this is saying the guards were not disoriented, but they wanted to change the rules so that they could all meet together at one tower while still making a transition to an adjacent tower each hour. How long would it take him to achieve that? So I didn't get the answer originally. I thought it was like a really simple problem where they could all keep moving to one tower and it would just take 5 moves to do that. The problem is that they must move one tower to an adjacent tower every hour. They can't stay in one place. So it's not like they could keep moving to, say, tower number 5, and as they get there, they don't move after that. They have to still keep moving. So that's what makes this a bit harder. So that's one hint. And the other hint is that try solving the puzzle where you have you have only 3 adjacent guards. So let's say they're at tower 1, 2, and 3. And you still have 9 towers, but you have these 3 adjacent guards. How long would it take them to get to the same tower, given that each hour they have to move to an adjacent tower? And that's sort of the key. When you solve this, then you can work back to the original puzzle, and it should be easy or easier. So I want to follow up with the hint I gave you first. Let's just say we have 3 guards. This is our tower. This is our wall around the castle, and then each vertex is a tower, just to make clear. And the dots are the guards. So let's say we have 3 guards, and we want to figure out how to get them all at the same tower. So the issue is that they, as I mentioned a few times, they need to move. So if this guard moved here, and this guard moved here, and this guard moved here, then you would get this configuration here. Let me just say it again. So this guy goes here, this guy, so these two basically go clockwise, and then this guy goes counterclockwise, and you get this arrangement here. Now, they can move together, so I'm going to just group these two as one, just to make it a little bit easier to draw. So let's just say that this is one here, and this is one, and these two, basically these two guys move as a unit from this point on. There's no advantage in separating them again. So the next move, an hour later, this guy goes. First of all, let me say this: if he tries to go here and they try to go there, they could just keep cycling forever. So that's not going to work. So basically, they start going in the opposite direction. So this guy goes here, and these two guys go here. And as I say, I'm just representing it as one guard. Then this guy moves here, this guy moves here. We have this, and then we do one more. He goes to here, he goes to here, and then they go together. And again, these two guys have been moving together, so you actually have all three here. So the problem reduces just getting those 9 guards to get into a configuration where they're only at 3 towers. It doesn't matter if you have 3 here and 3 here and 3 here. We're going to just treat them as one once we get them, together on a common tower. So we'll take this as a given. If we ever get all 9 of them into 3 positions adjacent to each other, then we know from this solution here that we can solve the problem in 1, 2, 3, 4, 5 steps. So we already have 5 steps that we know about. So I'll give you the rest of this solution on the next slide. So here's how I solved it. Now we have all 9 guards present at this point. And I suggested that we group these in groups of threes. And then we'll look at what happens to each one of these groups of threes when they move. So this is similar to what we had on the previous slide. These two guys go this here, and this guy comes back this way, and we get this configuration. Same deal here. Then this is almost the same, except you're going to move it out this way. So in other words, this guy and this guy move here, and this guy moves back here, and you get this. So now we have them at 1, 2, 3, 4, 5, 6. We have everybody grouped at 6 towers. Just to make the drawing a little bit simpler for me, I grouped these two together and these two together. As I mentioned before, there's no advantage in separating them. So this, I'm just using a shorthand to represent it this way here. Okay, so then the next hour, these two move clockwise, so here and here. This guy moves here, and this guy moves here. And so we have this configuration. And then these two will move clockwise again, so they'll be here and here. This guy, these two will move here, these two will move here. So we'll have them here. And now we have 3 adjacent to each other, and we can revert back to the solution on the previous slide, which required 5 more moves. So we have 5, 6, 7, 8. 8 moves is the minimum solution. We have an inheritance problem here. I've seen this different places at different times, and the idea is kind of similar. You may have seen it before, but if not, give it a try. So let me read through it. A recently deceased shepherd has indicated in his will that his eldest son is to receive 1/2 of his sheep, his middle son is to receive 1/3 of his sheep, and his youngest son is to receive 1/9. There is a problem since the shepherd's flock currently has 34 sheep. So we can't divide it based on these numbers, right? If we take a half, we get 17. That works out okay, but then you can't take 1/3 of 17 or 1/9 of it. So we're kind of stuck here with the problem. So how do we get around this problem of evenly dividing up to 34 sheep? I'll give you the answer on the same slide, so you may want to pause here. So I'm back. Here's the answer. It's kind of a trick, really. You pretend that you have two fictitious sheep, and so you go up from 34 to 36, and then the eldest son would get half of this, 18. The middle son would get a third, that would be 12. The youngest would get 1/9, that would be 1/9 of 36 is 4, and that adds up to 34. So you're not allocating any of the fictitious sheep to the three sons. And so once you've done this, you can make the fictitious sheep disappear, and you've fulfilled the fractions of dividing up the will. It's a little bit of a trick question, but it's kind of fun, I guess, to come up with the answer on this one. The alternate dice puzzle. Is it possible to relabel the faces of two six-sided dice with alternative positive integers to produce two dice with the same sum probabilities as ordinary dice? So just to be clear, we want to relabel two dice. They won't have the same numbers necessarily on the dice, on each die, and each of the possible rolls, so in other words, getting a 2, a 3, all the way up to a 12, would have the same probability as we have with the normal dice of just going from 1 to 6. And the source of that is a book by James Tanton, Solve This, Math Activities for Students in Clubs. So there's a lot of puzzles that can involve experimentation and people working in groups to figure out answers in this book. So I would recommend this. It's a good book. In fact, Tanton is a very good author of basic educational material for high school and college mathematicians. There's an infinite number of solutions to our dice problem if we allow for negative numbers. The top line here is the solution given by Tanton in his book. We have one die with the numbers 1, 3, 4, 5, 6, 8, and the other die with 1, 2, 2, 3, 3, and 4. So we have repeats, but they would be on different faces of the die. If you subtract 1 from each of these numbers and add 1 to each of these numbers, you get another solution. And let's check this one out to see if we get the same probabilities as we would get with normal dice. I'm not going to go through all these, but let's look at a few. Let's look at 7. With regular dice, normal dice, there's 6 ways of getting a 7, so the probability is 6 over 36, or 1/6. And it turns out to be the same here. You can see that. You roll a 2 here and a 5 on this one, a 3 here and this 4, or a 3 and this second 4. And then you can have a 4 in the first 3 and a 4 in the or a 4 in the second 3, and then finally a 5 and a 2. So there's 6 different ways of getting a 7 using these 2 dice, and that will give us the same probability as normal dice. You can look at a few more, like 2. The only way of getting a 2 is 0 and 2. So the probability is 1/36. We know for normal die, the only way is getting a 2 is the snake eyes, 2 1s. And then the only way of getting a 12 with normal dice or box cards, 2 6s. And with these oddball dice, the only way of doing it is a 7 and a 5. You may want to check a few of the other ones just to convince yourself that these are actually valid numbers to put on dice. We have another puzzle from the book by Tanton. Put the reference down here again. This one's kind of hard. It's more of a geometric type of puzzle. It involves grid tiling. So you have an 8x8 grid of squares, in other words, a chessboard or a checkerboard, and you want to be able to tile it or cover it with tiles of dimension 3 by 1, in other words, this type here, and 21 tiles of dimension 3 by 1. So that would give you 3 times 21, that would be 63, and then of course you need one more in order to make 64, and then there would be this one additional tile of size 1 by 1. So the question is it possible? And of course, if it is possible, then you would want to demonstrate that. So I'll give you a hint on the next slide, and then I'll give you the complete answer towards the end of the lecture. Okay, so let me give you the hint. Let's focus on the left here. I've colored the our 8 by 8 grid with white, green, and yellow squares. And the first thing I want to note is that if you put a 1 by 3 tile either horizontally or vertically anywhere you want, let's say here, you're going to cover a yellow, a green, and a white. No matter how you try, you could go up here. You're still, I mean, it won't be the same order, but you're going to cover a yellow, green, and a white. Yellow, green, and white. So no matter where you put your 3 by 1 tiles, you're going to cover three different colors, yellow, green, and white. That's one point. The other point is that if you count the number of greens in this, you're going to get 22 green, 21 yellow, and 21 white. So what that means is that that odd 1 by 1 tile is going to have to be green, because the 1 by 3 tiles are going to cover the other 21 green, yellow, and white, because of what I just mentioned about how they have to cover 3 different colors each time you lay one down. So that's one point. Then the key point here is that when you rotate this, that one, which I've done here, I've rotated this 90 degrees, and you can rotate it again if you like, and then a third time to get back to the original. But that one tile that has to go on a green spot, it has to go on a green spot here, same green spot here, and across different rotations. And the only 4 squares that are green after you rotate it are the 4 that I have the checks in. You can see, for example, this one here is, after the rotation, is not green anymore. But these remain fixed as being green no matter how many times you rotate the grid, and the 1 by 1 tile has to go into one of these. So the hint is to pick one of these. I picked this one, and the solution I'll give you at the end, and then just try to figure out how the 1 by 3 tiles fit around this to completely tile the square. Okay, so I'll give you the answer at the very end, but it's kind of a fun problem to play around with, and it took me around 10 to 15 minutes to finally get it, but I did eventually figure the solution out. We have another puzzle. It's called the Special Agents, and I've taken it from this book, which I've referenced quite a few times. I'm going to show you the solution in the next couple of slides. I got a different answer from what was given in this this book here, which makes me a little bit concerned, but I keep checking, and it seems like the answer in the book is wrong. And I know that at least some of the puzzles in this book were published in a magazine first, and I can't imagine if it was published to a wide audience that many people would have missed the error. So it's either I'm missing something, or two, maybe this was not one of the puzzles published in the magazine and the author just missed something. But have a look when I show you the answer and see if you agree with my analysis. So here we go. The puzzle is a special agent is to be selected from a row of 11 agents. The key here is a row. They're not in a circle. They're just one after the other in a row. The row contains exactly 3 special agents, and the special agents are equally spaced. So we don't know where they are, but we have these 11 agents, and so there's an equal number of agents between them. So that, for example, you might have a special agent, and then a non-special agent, a special agent, a non-special agent, and then another special agent. So there would just be one, agent between a non-special agent between them in that case. But there could be two or three, so forth. But they're equally spaced, or at least that's how I read this. And the question is, what is the minimum number of agents that we need to select to be sure of getting at least one of the three special agents? Okay, so have that think, and I'll give you a hint on the next slide and then solve it on the slide after that. So this is sort of a hint, or you could look at it as partial solution. I just put down what were the possible places for the special agents out of the list of, the total list of 11 agents. So one possibility is here. They could be 1, 2, 3, 4 apart. So there's 4 non-special agents between them, and there's only one way to do that. Then they could be 3 apart. So you have 3, 3, and then you have a couple spaces left over. You could shift, and you could shift again, but in each case you have 3. And then this one is 2. You notice 2, and then there's some spaces left over here. But then I just kept shifting it over until you got here. So as far as I could tell, this is the 1, 2, 3, 4, 5. There's only 5 ways of having 2 spaces, 2 non-special agents between the special agents. And then you have 1 space between them, and there's 1, 2, 3, 4, 5, 6, 7. So there's 7 ways of having only 1 space between them. So from this, you want to know what is the least number of agents that you select out of the 11 to be sure that you're going to hit at least one of these special secret agents. And I'll show you that, at least my solution, on the next slide. It doesn't agree with what the author of the book that I referenced on the last slide is saying. So here's my answer. I took the distribution tables from the last slide, and then I put in green what I thought would be the right solution here. So if you pick 5, 6, and 7 from that list, then no matter how the agents are distributed, no matter what row, what possibility, each row is a possibility, right? Each row has at least one X in this green region. You can check. Some of them have more than one X, but so if you pick 5, 6, and 7 out of the lineup, you're guaranteed to get at least one of the special agents. If you tried only 2, for example, if you pick 5 and 6, then you could miss here. If it was this distribution or this distribution, you wouldn't hit anyone. And you can look at any other combinations of just 2, and you won't, as far as I could tell, you won't be guaranteed to get a special agent. So my answer is 3, and it's these 3 in particular. The author of the puzzle book that I mentioned, he says 5, and I've read his solution, I don't know, a dozen times, and it just doesn't make sense to me. So if you have the book and you would like to inform me that I'm wrong, that I'd be grateful. Otherwise, I think this is the right solution. It may be that I'm interpreting the problem wrong, and if you think there's another way of interpreting the problem, let me know in the comments. There's several variations of these jug problems or glass problems where you have so much liquid in a larger container and you want to move it around between several smaller containers to get an exact measurement. In this case, we have 2 friends have an 8-quart jug full of water, and they wish to share it evenly. They have 2 empty jars, one that can hold 5 quarts, and the other is able to hold 3 quarts. How can they measure exactly 4 quarts? So they can only use the jug and these 2 empty containers, and they can't estimate. Like, you can't estimate filling it halfway up. You can you can take water from this larger jug and completely fill this to 5 quarts and then dump it into the 3-quart one until it gets full, and that will leave 2 in this here. You can do that type of thing to break up the measurements. So I've seen this in many places. There's a site called Cut the Knot. I've given the link here, and that has this, and along with a lot of other problems. This person was keeping this website up for quite a long time, but he passed away a few years ago. So the site remains, but I don't believe anyone's updating it. It's a pretty good site for puzzles and mathematical theorems and so forth. So you may want to have a look there. I'll give you the answer at the very end of this presentation for this puzzle here. This is a rather difficult and elaborate puzzle. From what I've understand, the source of the puzzle isn't known, but it's used in various interview processes at high-tech companies. I can't imagine even a very bright person just coming up with an answer to this at an interview where they only have a few minutes. But I guess maybe the intent is to just see how someone deals with a very difficult problem and how far they can get, what type of reasonable statements they can make. So we're not under that condition. We can you can pause the video once I explain this, and then you can take as long as you want to work on it, and then I'll give you the solution. So a rabbit is placed hidden in one of 7 hats that are lined up in a row. At the end of each day, the rabbit can move either one hat to the left or right, except when the rabbit is in hat 1 or 7. So if it's on either end, then the rabbit would have to move back in. So if it's in under hat 1, I would have to move back to hat number 2 the next day. And then when the rabbit is in hat 7, or under hat 7, it would have to move under hat 6 the next day. In any event, the rabbit must make one move per day based on the rules stated above. You're allowed to make one guess each day as to the location of the rabbit. Is there any way you can be sure to find the rabbit? Seems impossible, but it is possible to solve the problem. So we have the setup of the problem here. We have the 7 hats, and I've shown the rabbit here, but it's actually under the hat. And you don't know where it is, and you get one guess every day. And in the evening, the rabbit switches hats, but it has to go either right or left. And when it's in 1, it has only a choice to go to 2, and when it's in 7, it only has a choice to go to 6. So what we're going to do is solve a simpler problem, and then we'll reduce the overall problem to this simpler problem. So what we'll do is consider the case where the rabbit starts in an even numbered hat. And we'll proceed as follows. On day 1, when we make our first guess, we'll guess that the rabbit's under hat 2. And if we're right, it's all over and we're done. If we're not right, then it's either under 4 or 6 based on our assumption. So at the end of day 1, the rabbit will move from 4 to 3 or 4 to 5, or if it's in 6, it'll go from 6 to 5 or 6 to 7. So the rabbit will be in 3, 5, or 7 on day 2 when you make your second guess. And you guess 3, and if you're correct, then it's over. If not, you know that the rabbit's under 5 or 7. Then that evening the rabbit moves again, and it can either go from 7 to 6 or from 5 to 4 or 6. So it's either in 4 or 6 the next day when you make your next guess, and you guess 4. If it's in 4, you're right, and you've won. And if not, it must be in 6. And then that evening the rabbit can go to either 5 or 7. So your next day, you would make your guess to be 5. If the rabbit's there, you win. If not, it must have been in 7. And then that evening, the rabbit has only one choice, to go back to 6, and then you guess 6, and you're guaranteed to be correct if your assumption of the rabbit being under an even number hat was correct. Now, if that wasn't correct, then we need to figure out how to solve the problem in that case. And it basically comes down to reducing the problem to when the rabbit eventually gets under an even number of hat. We'll talk about that on the next slide. So if the rabbit started under an even numbered hat, you should catch the rabbit by day 5. That's what we showed on the previous slide. If the rabbit started under an odd number hat, and given that the rabbit must alternate between even and odd numbered hats, we know the rabbit will be under an even number hat on day 6. So it's basically, you just count it on your fingers. It's odd, even, odd, even, odd, even. So on day 6, the problem reduces to the even start problem that we solved on the last slide. So a general solution would be to use this sequence that I'm showing here. You guess 2, 3, 4, 5, 6. That's what we did on the previous slide. If the rabbit was started underneath an even numbered hat, you would find the rabbit by day 5. Then on day 6, we know what it would be under an even number hat. So we just repeat the 2, 3, 4, 5, 6, and that would guarantee that we would get the rabbit by the end of the 10th day when you make your 10th guess. So that's a sequence that will guarantee finding the rabbit, which is, to me, a bit hard to believe because it seems impossible when you first look at this, but it does work as we demonstrate it. And there's other solutions here. We could have started on the opposite end and have done 6, 5, 4, 3, 2, and then do 6, 5, 4, 3, 2 again. Or we could even mix these two sequences. We could do 6, 5, 4, 3, 2, and then 2, 3, 4, 5, 6, or 2, 3, 4, 5, 6, and 6, 5, 4, 3, 2. So we have 1, 2, 3, 4 different solutions. There's a few more puzzles you could try that are similar to this. Try the problem with 6 hats and see how that works. And then you could try it in general with n hats, and the solution will look something like these sequences here, except instead of having 5, you'll have n minus 2 guesses on each side of this sequence here. There's also a YouTube video that goes into this in a little bit more detail from Mind Your Decisions. I will locate that video if I can, and I'll put it in the information below this video when I post the video. We're back to the fill in the circles puzzle. I'll give you a few more hints, and then I'll give you the solution on the next slide. So the first hint I gave you was this one here about having to have 8, 9, and 10, because that's the only way you can add the 27. And if you have 8, 9, and 10 here, then this could be, of course, 8, 9, or 10. If this is 8, this must be 5. If this is 9, this must be 4. And if this is 10, this must be 3. So this circle here must be 3, 4, or 5. So that gives us another hint. Then this one here can't be 8, 9, or 10. And it also can't be 1, 2, 3, or 4, because if it's 1, then you can't use an 11 here to get up to 12. We're only allowed to go from 1 to 10. Same problem was 2, because 10 is taken. Can't use 3 because 9 is taken, and we can't put a 4 in here because the 8 is taken. So we have to use 5, 6, or 7, but 6, you would need to repeat it. We're not allowed to repeat, so we're only left with 5 or 7 for these two. So that narrows it down quite a bit. So if you put a 5 in here, then you would need a 4, and if you put a 7 here, you would need a 2 in here. And you can do the same game with this. I won't explain that, but you could see how that would work. So we've eliminated a lot of the possibilities for these circles, and I'll leave it to you to do the final solution, which I'll show you on the next slide. Okay, so here we have the final solution. We can check it. It's 5 and 7 is 12. These add to 27. We saw that already. 1 and 6, 7, 9, 13. That's good. Coming down, we get 13, 11, 9. This is what, 8 and 10, 18. 10 and 12 is 22. So everything checks out here. In the grid tiling solution, you remember the hint I gave you that the 1 by 1 tile had to be in this square, this square, this square, this square, and I picked this one. And then I went about trying to find the 1 by 3 tiles to tile the rest of this. And you kind of have this cyclic pattern around the 1 by 1 tile, and then after that it's fairly easy. The bottom is really easy. You just put the 1 by 3 tiles in a row like that, and then this corner up here is not much harder. You use 2 this way and 3 that way. So the hard part was figuring out how to complete this part in here. So on our last slide, I have a solution to the 3-jug problem. If you recall, we had an 8-quart jug full of water, and we had a smaller jug of 3 quarts and another jug of 5. They were both empty, and we needed to use the 3 quarts to balance out exactly 4 quarts for each of 2 friends who wanted to share the water equally. And we had the restriction that we're not able to estimate, so we couldn't, for example, go to the 5-quart container and kind of eyeball it and say, oh, this looks about 4 quarts, and stop. All we could do is fill these containers and transfer between them. So let's look at the solution. We first fill the 3-quart container, then we transfer that to the 5, then we refill the 3-quart container. So at this point there's 2 quarts left in the 8-quart container, which we can use if we need to, and we will. We will need to put water back into it, as you'll see. So before we do that, we take the 3-quart container and fill this 5-quart container to the top, as shown here. So this just has 1 left, and we've added 2 more to this. And there's 2 left in the 8-quart container. When we take these 5 quarts and put it into the 8-quart container, and we get this configuration here. This one's empty, and then 7 quarts in here. Then we transfer the 1 quart from the 3-quart container to the 5-quart container. We refill the 3-quart container from the 8-quart container. That's this. Excuse me. And we're almost done. This has 4. We just need to take these 3 quarts and put them into the 5-quart container, and that finishes the problem. So that was the end of this lesson, and the last lesson that I've planned for some time, unless I get some comments or suggestions, I think I'm going to stop here at lesson number 13. So if you have any ideas, let me know, and thanks for listening.